The ground moved again beneath Hawaii's Big Island. On August 17th, a magnitude 4.1 earthquake struck near the south flank of Kilauea. The earthquake occurred about 7 kilometers below sea level, and by itself, a magnitude 4.1 earthquake isn't necessarily extraordinary. But this isn't an ordinary place. This is Hawaii, and beneath this part of the island sits one of the most closely monitored volcanic systems on Earth, Kilauea, a volcano capable of producing earthquakes, ground deformation, volcanic gases, and eruptions. So when a magnitude 4.1 earthquake suddenly appears beneath its south flank, people naturally start asking questions. Was this earthquake connected to Kilauea? Did something move underground? Could magma be involved? Or was this simply another earthquake produced by the constantly changing crust beneath Hawaii? And there's an important reason those questions matter, because with Kilauea, the earthquake itself isn't always the whole story. Sometimes the real story is what happens afterwards. So let's start with the earthquake. On August 17th, the Big Island experienced a magnitude 4.1 event near Kilauea's south flank. The earthquake was deep enough to be described relative to sea level rather than simply as a shallow surface event, and that location immediately matters, because this is not just ordinary ground beneath an ordinary mountain. Kilauea is an enormous volcanic structure. Its underground plumbing system is constantly being studied. Magma moves, pressure changes, the ground can deform, and earthquakes can occur as the crust responds to those processes. But here's the first important distinction. An earthquake near a volcano does not automatically mean magma is rising toward the surface. That's a common assumption. But volcanoes are much more complicated than that. An earthquake can have a tectonic cause. It can result from movement along a fault. It can be related to the movement of a volcanic flank. Or it can sometimes be associated with processes happening inside the volcanic flanking. So scientists can't simply look at the magnitude and say that earthquake was caused by magma. They need more evidence. And that's why the location of this M4.1 matters. It occurred on the south flank of Kilauea. The south flank is one of the most interesting parts of the volcano. Because Kīlauea isn't a rigid block sitting perfectly still on the ocean floor. It is a massive volcanic structure, and enormous volcanic structures can move. The weight of the volcano interacts with the crust beneath it. Sections of the volcanic edifice can shift. Faults can accommodate that movement. And earthquakes can occur as the structure adjusts. Scientists have documented movement of Kilauea's south flank toward the sea. That means earthquakes in this region aren't automatically mysterious. There are known geological processes capable of producing them, but that doesn't mean every earthquake can be explained instantly, and that's where this M4.1 becomes interesting. Because magnitude is only one part of an earthquake's identity. When most people see an earthquake alert, they look for one number. 4.1, maybe 3.8, maybe 5.0, and then they decide whether the earthquake was big. But scientists look at something much more complicated. They look at the earthquake's depth, its exact location, its seismic waveform, its relationship with nearby earthquakes, whether the event is part of a larger sequence. Think of it like a fingerprint. An earthquake isn't just a number, it has characteristics. Those characteristics can help scientists understand what happened underground. For example, imagine one earthquake occurs several kilometers beneath a volcano, then several more earthquakes appear nearby. Then the earthquakes begin moving upward. At the same time, the ground starts deforming, and volcanic gases begin changing. Now scientists have several independent signals pointing in the same general direction. That's much more interesting than one earthquake by itself. But imagine something different. One earthquake occurs. A couple of smaller events follow. Then the activity fades. The ground doesn't show an unusual change. Gas emissions don't show a major change, and the volcano's other monitoring systems remain relatively stable. That tells a very different story. And this is why scientists don't judge volcanic activity using one signal. They look for patterns. Kīlauea is monitored constantly. Seismometers detect earthquakes. GPS instruments measure tiny movements of the ground. Tilt meters can detect changes in the slope of the volcano. Satellites can observe deformation across much larger areas. Scientists monitor volcanic gases, and they observe surface activity. Each system provides another piece of information, and together, they create a picture of what the volcano is doing underground. This is important because Kilauea is already an active volcanic system. There have been earthquake swarms around parts of the volcano. There have been changes in seismic activity. There have been periods of ground deformation. And there have been eruptive episodes. So the presence of earthquakes near Kilauea isn't itself a surprise. The real question is whether the earthquake represents a meaningful change in the volcano's behavior. That's a much harder question. And it can't be answered by looking at the M4.1 alone. We have to look at everything around it. Where did it happen? How deep was it? What happened before it? What happened after it? Did additional earthquakes appear? Did the earthquakes become more frequent? Did they migrate? Did the ground begin deforming differently? Did volcanic gases change? Did tremor change? And did surface activity change? Those are the fingerprints scientists care about. And this brings us to one of the most important ideas in volcano monitoring. A volcano is a system, not a single event, not a single earthquake, not a single eruption. A system. Imagine the volcano as a huge machine beneath the surface. We can't see most of the machine directly, but we can observe its outputs, we can measure vibrations, we can measure movement, we can detect gases, we can observe changes at the surface. And from those signals, scientists try to understand what might be happening underground. That's why one earthquake can be interesting, without necessarily being alarming. And current information surrounding this M4.1 is important here. The earthquake itself does not establish that Kilauea suddenly became more dangerous. There has been no clear evidence from this event alone that the volcano has suddenly shifted into a dramatically different state. Reports based on USGS information indicate no apparent impact on Kilauea or Mauna Loa from the earthquake. That's a crucial detail, because the headline can make an earthquake sound like a dramatic volcanic warning. But the actual scientific picture is more measured. The earthquake happened. Scientists can study it. But that doesn't mean the volcano suddenly changed its behavior. And this is where good science becomes different from social media speculation. A dramatic headline asks, "Is Kīlauea about to erupt?" A scientist asks, "What changed?" Those are very different questions. The second question is much more useful, because Kīlauea is already active. Scientists aren't waiting for the volcano to become active. They are watching for changes in its activity. That's the key. If earthquake activity suddenly increased and remained elevated, that would matter. If earthquakes began migrating towards the surface, that could matter. If ground deformation increased significantly, that would matter. If volcanic gases changed at the same time, that would matter. And if several of those signals appeared together, scientists would have a much more interesting situation to investigate. But even then, it would not necessarily provide an exact countdown to an eruption. That's another important point. Volcano monitoring is not the same as having a crystal ball. Scientists can identify signs that a volcanic system is changing. They can estimate the likelihood of future activity. They can compare current behavior with historical patterns. But nature doesn't always provide a clean sequence of events. Sometimes signals increase and then fade. Sometimes a storm continues without interruption. Sometimes deformation changes without immediately producing surface activity. And sometimes a volcano remains active for long periods without producing a major event. That's why scientists watch trends, not isolated moments. And that brings us back to the M4.1. Did this earthquake change Kilauea? Based on the available information, there's no evidence that this earthquake by itself caused a dramatic change in the volcano. But that doesn't mean scientists stop watching. In fact, monitoring continues precisely because the volcano is active. The earthquake becomes another data point, another measurement, another event that can be compared with everything else happening beneath the island. And this is where the story gets bigger, because Kilauea isn't just a volcano sitting on an island. It is part of Hawaii's enormous geological history. The Hawaiian Islands were built by volcanic activity. Magma rose from deep within the earth. Repeated eruptions built mountains from the ocean floor, and over enormous periods of time, those volcanic structures became islands. But the process didn't simply stop after the islands formed. Hawaii remains geologically active. Earthquakes happen. Volcanoes erupt. Volcanic flanks move. Crust shifts. And the landscape continues changing. That means an earthquake and volcanic activity can exist together without one automatically causing the other. This is important because people often see the words earthquake and volcano in the same sentence and assume there must be a direct connection. Sometimes there is, sometimes there isn't. Scientists have to determine which explanation best fits the evidence, and that's why the M4.1 is worth watching, but not worth turning into a prediction. So what would actually make this situation more significant? Scientists would look for sustained changes, not just a single earthquake, not just one unusual reading, but a combination of signals. Imagine earthquake activity increasing for an extended period, then imagine the earthquakes becoming progressively shallower, then imagine the ground beginning to deform, then imagine volcanic gas emissions changing, and finally, imagine surface activity changing as well. Now you have multiple independent observations that would be far more significant than one M4.1 earthquake. Because when different monitoring systems begin telling the same story, scientists have more evidence that something inside the volcanic system may be changing. But even then, there is uncertainty. Scientists may be able to say, activity is increasing, that they may be able to say, the volcano is undergoing a significant change. They may even raise alerts or recommend precautions when the evidence warrants it. But the exact timing of an eruption can still be difficult to determine. That's because volcanoes don't behave like clocks. They behave like complex geological systems. And Kīlauea is one of the best places on Earth to study that complexity. For decades, scientists have built an enormous record of its behavior. Earthquake sequences, eruptions, ground deformation, gas emissions, lava movement, fault movement. If every new event can be compared against that history, and that history is extremely valuable, because scientists don't have to start from zero every time the ground moves. They can ask, have we seen something like this before? How did the volcano respond? How long did the activity last? How it happened afterward? Those comparisons help turn a single earthquake into something much more useful, a long-term scientific record. And that may be the most important thing to understand about this M4.1. The earthquake itself isn't necessarily the story, the response of the system is. If nothing else changes, the earthquake may eventually become another entry in Hawaii's enormous earthquake catalog. But if other signals begin changing, scientists will notice, and that's why they keep monitoring. Because the most important signal isn't always the loudest one. Sometimes it's the combination of several small changes, a little more seismic activity, a little more deformation, a subtle change in gas, a shift in the location of earthquakes. Individually, each signal might not mean much. Together, they can tell a very different story. So where does that leave us right now? A magnitude 4.1 earthquake occurred near Kilauea's south flank. It was about 7 kilometers below sea level. It was large enough to attract attention. But it does not, by itself, prove that magma is rising toward the surface. It does not prove that a major eruption is imminent, and it does not establish that Kīlauea has suddenly entered a dramatically different phase. Current information indicates no apparent impact on Kilauea or Mauna Loa from the earthquake itself. So there is no scientific reason to turn this single event into a prediction. But there is also no reason to ignore it, because Kilauea is an active volcanic system, and scientists are already watching it closely. They will continue monitoring the earthquakes. They'll monitor the ground. They'll monitor deformation. They'll monitor gases. They'll monitor tremor. And they'll watch the surface. The earthquake has happened. Now comes the part scientists care about. What happens next? Does the activity fade? Does another swarm develop? Do earthquakes become more frequent? Does their depth change? Does the ground begin moving differently? Do several independent monitoring systems begin detecting the same change? Those are the questions that matter. Not the most dramatic headline, not the biggest number, not the scariest prediction. The data. Because that's how scientists distinguish an ordinary earthquake from a meaningful change in a volcanic system. And this is also why the phrase Kīlauea isn't done yet needs to be understood correctly. It doesn't mean a massive eruption is guaranteed. It doesn't mean an eruption is coming tomorrow. And it doesn't mean this earthquake triggered something catastrophic. It means something much simpler. Kilauea remains an active volcano. Its underground system is still being monitored, its geology is still changing, and scientists still have to watch what happens next. That's the real story. The M4.1 earthquake is one data point. The volcanic system is the bigger picture. And the next few days or weeks could provide more information than the earthquake itself, because if the activity returns to normal, that tells scientists something. If it increases, that tells them something else. If the location changes, that's another clue. If deformation changes, another clue. And if several signals begin moving together, then the picture becomes much more interesting. That is how volcano science works, not by predicting every earthquake, not by turning every tremor into a disaster, but by collecting evidence, comparing it, and watching for meaningful changes. So, did the M4.1 earthquake mean Kīlauea is about to erupt? No, not based on the evidence we have, but does it mean the volcano should be ignored? Absolutely not. Kīlauea remains an active geological system, and scientists will continue watching it for the signals that matter. The earthquakes, the deformation, the gases, the tremor, the surface, and most importantly, the pattern. Because one earthquake can be interesting, but a changing pattern can tell a much bigger story. And that's why this earthquake isn't really the end of the story. It's the beginning of another observation, another measurement, another piece of evidence. The ground moved. Scientists noticed. Now they're watching to see what happens next. Because with Kīlauea, the most important signal isn't always the earthquake you just felt. Sometimes, it's the pattern that begins forming afterward. And when the next signal appears, that's when the story gets interesting again. If you want to follow Kīlauea's activity without the hype, subscribe and stay with us, because we'll be watching the data, not just the headline.